Okay, so we'll get into rigid body in chapter 16. We'll study the kinematics again on the plane. Okay, so here are the objectives. We'll touch up the various types of the motion for these bodies on the plane. Then we'll get into translation, of course, and then your angular motion, because that's the only major way of moving, okay, any body. Then we'll get into the absolute motion analysis. Of course, you don't have to do calculations, all right, in this course, because we're just hitting the concepts. So don't worry about any heavy calculation. Then all motions, you always have your position, your velocity, your acceleration. So we'll get into that. So the only difference is the particle is now the rigid body. All right, the path is a planar. So we're thinking about translation like a plane. Planar mean on the plane, okay, and then your angular, your rotation again. And we will bring in all the aspects of kinematics. So position, velocity, acceleration, always there. Yeah. Each of them you have average, instantaneous, constant. All right, three major types of kinematics for each quantity here. Then we'll touch up the center of zero velocity, and then on. Of course, this is you don't have to calculate. This is trying to find the velocity value. Okay, on a point, on a body, using that method. Again, this two, we'll just talk about it, and if you listen to it, you're cool. And then the rest of them is just a relative motion analysis, because motion is, again, there are so many different types of motions going on at the same time, right, in the space. So conceptually, you have to be so aware of where you are, what types of bodies are out there, even though we call them bodies, just objects, particles, right? And they're everywhere around you, and you're exerting force on them, and they're exerting forces on you. And we balance them out all together with our energy. Okay, each body has some form of energy, because without that energy, it can't be able to take a position or stay in a space or move even. Yeah. So if you take away the energy from the existence, there wouldn't be any existence. Yeah, we'll go back to something that we don't know, which is imagine a phenomenon without any motion, zero motion, right? It's going to be very different nature from everything that we know here. Okay, all right. So rigid body, I'm gonna make my lecture really easy for you, so that way you won't get heavy things. So let's just go with, okay, we have like three different ways the body is going to move on a plane, right? So the very first one is it's going to move, and we call this movement type 1 translation. Okay, second one, translate means just going that way. Rotation, like rotating about. Since you're rotating, then there is an axis, because without the axis you cannot rotate. See, like how, so you've got to put your mind when you are studying. You can just take the word language, it doesn't really work in science. It's your intelligence. Okay, science is your intelligence. You have to think with it, or you will end up just getting words right there. You won't get the deeper meaning of it. So the deeper meaning of each one of them, every time you read it, think. Okay, think with your brain. You have a very powerful brain. Okay, but most of us don't use it. We're just using like daily stuff, like family stuff, school stuff, work stuff, money, and that's really not necessary. We come to school not only get a diploma to get a job. We come to school to think, okay, to nourish our brain and to practice our brain in thinking. Believe it or not, it's another type of movement. Thinking is a movement of your electrons inside of your body, which is the places your brain. Okay, so the way that we move the particles in the brain is by thinking. So your nervous system, yeah, you have to constantly move it. So the more you think, the more motion you get in your brain, and they move. When they move, the DNA, okay, and the RNA in your genes, that's pretty intact. Otherwise, it's gonna go stall, just like your muscle. If you don't move a muscle, it will go stall and become weaker over time. Okay, so make sure you think when you read. So let's go back here. Your rigid body moving on a plane. We're thinking about how many ways this rigid body can move on like a plane. So this is translation. Move it that way along the line, parallels movement, rotation, moving about an axis, and just the rest of the moving we call it general plane motion. Okay, just a plane motion. Then when you study, each word is so important. You got to get the deeper meaning of it. Rigid body, think. What is rigid body? Plane. Plane is like a flat, right, surface. So when a body is moving on a flat surface, so close your eyes and think about how a body is moving on a plane. Okay, like a plane. Just for now, just think like a plane. Move like a plane. Okay. All right. So let's go to the next slide. This is just the knowledge linking to the real life, so where we use or where we apply, all right, this concept. And of course, these are theories. We apply it in gears, cams, mechanisms for your mechanical operations, right? All the products that are dealing with the motion. We're gonna use this, right, types of motion and apply these principles, theories, calculation to do, all right, operations, and then into these parts. Okay, now we'll get into planar motion, right? So your body is gonna move like a plane, in a plane, on a plane. Think about it, okay? So how that planar motion is going on is, again, this little phrase right there, all the particles of a rigid body. How powerful that is. Don't just read it, okay? Put your mind with it. So when you think about the body, we're just thinking like a body, but there are gazillion stuff inside of that body. Okay, each one of them is also moving. Of course, we always give you the classical example of you, which is your body. And of course, that isn't that rigid because that's a biochemical body. But then, like your body, the same thing, right? Any rigid body is made of material. So we link it back to chemistry again. Remember your periodic table elements. That's all we've got. That's all we know, right? For now, up to this today, yeah. So your body has so many particles in it. These particles inside, they are kind of loosely bonded. All right. There's no such thing as a permanent or connected, seriously connected bond. All right. It's just like the bonds are they're just staying aggregation. I will call it aggregating together. Right. But the particles are too small in some of the bodies that you can't, like, as soon as you see a body that's, there are gazillion, I mean billions and billions and billions and billions of particles right inside of that material. You can't be able to see it or feel the motion of these particles either, but it's in there. Okay, but it is in there. Um, so we gotta generalize it. That's the reason why the exact thing there isn't in the world. Okay, every time we try to calculate something or try to think about something, we have only like a accurate, right, accuracy. That's about it. Yeah. So there's no absolute truth today up to today that we know so far. Yeah. Of course, again, that knowledge is limited to our structure, how the capability of a human structure. Yeah, we call it our body structure because it is a structure like a body. It's built with so many things inside of us. Okay, so it's still limited to that. So the think about it. I'm gonna think about the motion. You can't think only just a straight rigid body. You have to know that there are particles in that rigid body, and it's gonna move along the paths. See this word paths? That's the level of thinking you've got to put in mechanics and dynamics. Okay, so it's not that light. Yeah, so the subject is, of course, we gotta make it very easy for you to pass your test, and if that's all you care about, you're great. Don't worry too much about on it. Worry about getting it, all right, getting the concept of it. If you can, of course. If you can, who cares? That's your life. You can do whatever you want to do. As teacher, we have a duty to give it to you. Yeah, because out of 100 students, one of them might actually get it. Yeah, if one person get it, that's a lot in science. Trust me. So particles of a rigid body again move along paths which are equidistant from a fixed plane. Okay, so you have the particles inside of the rigid body. Even if we're talking about rigid body very loosely, you gotta think about these particles are moving along, right, in their own paths. And these paths again are equidistant. We have a measuring reference plane right there. Okay, so from the plane, they all are at the same distance and they're gonna move along the paths. Okay, so that's what we're talking about, and we will go into different examples to be able to see it. Okay, so three types in the planar motion for your rigid body. Again, every time I say rigid body, in your mind, you have to have the particles in that body. Particles in the body. There is a plane. There is a equal distance. Okay, and we're gonna break it down into three types. Right? At least you gotta get that conceptually. Yeah. So translation. So this type of motion occurs when a line in the body. Again, here is your body. There's a line that's going to remain parallel to its original orientation throughout the motion. Okay, so I don't know what's original orientation. Oh, it's got to, I know that it's something parallel to this thing. Yeah. So that's what you get, yeah, inside of your head. But that's okay for now. So again, we go back into to really think. And the line, we have a body line. So I told you I started to give you, right? We've got to draw. So in your head, oh, there's a line, right? So that's what you have to do when you study. You can just sit down or read and thinking about me and blaming it on the professor like that. You gotta draw like this. Okay, when you, of course, you're doing it with your hand, either on a paper, do whatever you want. I am very familiar with just drawing on here because most of the time we're on the computer, right? So it's up to you whatever you want to do. Yeah. So I would suggest, because in science we have to draw, so to be able to visualize it. Okay, so there is a body, it's talking about the line. So a line in the body is gonna remain parallel. It's a parallel. Okay, so that line is gonna remain parallel. So make it parallel with what? So continue, yeah, to its original orientation, mean positional or direction. So if that's going in this direction, then that is the original direction. All right. If that's a point, then you can have a point, right, in the original orientations. Okay. So if this is orientation, then there's a line for the orientation, and this thing is going to move along the line that is parallel to the original orientation. Okay, so I can make another line like that. Yeah, so now this move from here to there, see, but the line of movement is still it's a little bit difficult to draw on the 2D, but you kind of imagine like that. Okay, the line is parallel to the original orientation throughout that motion. So that's where you get it. Then we go back to here. In order for planar motion to happen, yes, you've got to have a particle, so thus we can make it like a little point. We can understand like that, right? Because we, instead of like drawing like so many circles, we can just make it a little dot, right, in the rigid body. So that also got to move along the path, see, which are equidistant from a fixed plane. Particle inside of the body that's going to move along the path, which is like this, okay, a little line like that, and that's going to be the equidistant from a plane. So there is a reference plane right there we are thinking about. All right, so we can also make a plane, yeah, like that. So there's a, just put a little, okay, um and let's just make the plane no fill line, so you kind of get that kind of idea. Okay, that's what you have to do. Okay, this is, of course, it's a very simple, sketch or diagram, but then you kind of get it. So now we'll get into the real drawing, right, with the animation. This is from the textbook. And then we're going to break it down. Even in the translation, we have two things going on because the way the motion moves, I mean, different kinds of, like movement. So we break it down into two modes, yeah? So you have planar motion come to translation, the first type. In translation, we have rectilinear, okay? Rectilinear, I mean, you can break it like this, yeah? Recti and then linear, like that. So something going along the line, right? Linear on a path. So you got it. So recti, how's it going? It's dealing with the parallel, right, movement, like this. See, there's a little dot, right, describing a particle. That particle can be here, 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 here. Yeah. So when you go to graduate school, the problem get harder and harder, more complex and complex, and it's going to take you like about a week or two to do it. It's because that particle can move here and here. So as soon as that particle move here, it's not like a 90-degree straight. It's like coming into a different positioning. We call it positioning on your 3D axis. See how complicated movement can be if you think about one single particle in your rigid body. So anyway, so right now let's just go with a very, very simple thing like that. See, like this, okay? And this body is gonna move, bang, and we call that translated. The body has been translated from here to there. In which way? In a rectilinear way. Why? Because we are breaking down into only 2 points, concentrating. Not all the gazillion points are in there, don't have a mental power or intelligence to do that. So we're going to go with a very simple 2 points on the body, okay? And they are parallel, right? We make it parallel, make it simple for us to be able to study that type of motion. Yes, of course, parallels are therefore 90-degree to each other, yeah, because your geometry, so every parallel point, also the point on a line that is parallel to another point on the line. So these two lines are parallel, the points are on each line, they are at 90-degree always, okay? And then you move it. So the motion is called that type of motion, okay? Just bang, move right here. Yes, and we call that the rectilinear. Yeah, rect mean like very much talking about just on a straight line at 90-degree parallel to each other. Yeah, translated. This point, original orientation, same point, go on to the same direction to that. Okay, there's a line in your body across a particle in that body. Yeah, and that is moving. Where's the plane? So the plane is just right there. Okay, right here. See, like how this little thing drawing like that. See that? It's not like just a straight line. Okay, see this little one? We're drawing like this. That's your reference plane. Yes, equidistant. Yeah, from here to here, totally equidistant. And then move this position to the final position. So that's your rectilinear translation. Okay? Don't think like that's the only type of motion we have. No, that's just a 2 point that we selected to simplify things and break it into a very simple, the very first type of translation. But as you go study more and more, more and more, all the way to the end of your life, if you choose this lane, yeah, dynamics, then that point is going to be everywhere. It can be anywhere. Of course, it's not going to, your body type is also different. Why? Because the material of your body different. The position of the points that you're considering different. All right, and also the shape also coming in. Yeah, so your calculus stuff. So anyway, so at least conceptually, you have to get this. Yeah. Don't just swallow up this one and try to remember everything and write it back down. Yeah, try to make it like your own word, right? And show me what you understand. I don't really reduce a lot of points, even if you're writing so off. I might reduce like 1 or 2 points or 0.5 or something like that to keep your grade. But yes, but your effort, right? You put effort in thinking, and at least you put yourself in a stress position and you write it out. That's I'm giving you grade for it. Okay, not just the correctness of your understanding, because it will take about 2 to 3 years to actually get it. Okay, so anyway, so right now it's just a very first step. The next one, another, yeah, and then you separate like this. So curve, see, curvy, linear. So this is now another, yeah, condition. Again, very simplified because we're dealing with only 2 points again, yeah. The path of the motion this time, instead of straight 90-degree parallel to each other, we're gonna have it curve. Because in real life, nobody is moving rigidly with 90 degrees straight, yeah? Everybody is moving like going in a curve, wiggly lines, yeah? And then ding, ding. So there are many different paths. If you think about how you're driving, yeah? Sometimes there's a curve and it's going to tell you, oh, there's a warning, right, sign on the side of the road, there's a curve. So if you think about the environmental factor, so there's winter, there's rain, there's fog, all kinds of you don't understand. There's a curve ahead of you, yeah? So you might be like moving on a straight line like this, and all of a sudden you have to curve, so be careful, yeah, with your velocity and acceleration, things like that, yeah? So anyways, so now you have here curve. We're gonna go along the curved lines. Again, just put it two, okay, for your simplification with a two little particle right there. Yeah, bang, translated on a curve, path lines. Okay, and don't forget your plane, because there is a plane right there. It's just plane is curve. Yeah, going that way. And we call that a curvilinear translation. And when we actually calculate the things, of course, we put the plane into it because you need a reference plane for the distance, okay, for calculating the distance. Oh, all right. So that's with the first type, yeah, translation. For your planar motion, how the rigid body moving. First type of motion. So now let's get into second type. Second type is we will study how the body is rotating about a fixed axis. Okay, again, don't forget your plane, don't forget the point. No, the point, reference point that we are studying, concentrating, is not on the axis, it's around the axis. Okay, since we're dealing with the axis, you have circles, okay? Circles, so your geometry. Circles and your point, again, we want to imagine a single point to simplify, yeah, on that circle. Okay, so we imagine two for simplification, 2 points, reference points, and that is going to rotate, okay, rotate about a fixed axis. Okay, rotation, rigid body rotates about a fixed axis. What's going on inside? There are so many particles in the rigid body. All the particles of that body, okay, except the particles right here at that line. Again, incredibly powerful, powerful phrase right there. All the particles of the body except those which lie on the axis of that rotation. Meaning like the particles right here isn't moving when a body takes a rotation. Because you cannot get a rotation if one of the particle along that fixed axis is moving, by the way. Alright, we can see that. We can see these particles moving at or because of the material and the level, the size, because you gotta understand which level you are living. You're living at a human level right there, meaning like your body is a very complex structure. Your body is not simple like this, okay? Your body has organs right inside of you. So you're actually the result you're actually the resultant total, okay, interaction of all the interactions of your body, everything inside. Or how strange that is. You're powerful, actually. We're so powerful. If you think about it, even if you think about sense of motion, that's the power we've got, right? We're not just moving with one single energy. You're moving with billions and billions of contributed forces and energy coming out within from your uh, each particles are inside of your body, just like that. Because now we go back to here with particular element right here. Of course, they have different types of bonding that we go down straight into that body, and there are particles, right, adjacent to each other, right. Go back to your chemical again, chemistry again, in there. They don't move. More interestingly, they're kind of like just staying, meaning like the movement along that line is not as much as the movement outside as soon as the body rotates. Okay, so anyways, that's what the rotation about an axis means. Don't say like, oh yeah, the body is rotating on an axis, but you gotta understand the particles inside of the body. There are two separate groups going on in there. One is along the axis, and the other one is along. The other one is anywhere in the body, okay, except the axis line. The particles on this line don't move. The particles on this line moving about the axis. All right, I think you get it, and we call that the rotation about a fixed axis. You're not dealing with the body, even though we call the rigid body. We go into the particles inside of that body, and they're gonna move along again the path. Yeah, we have two different paths already. One is a straight 90-degree to each other, parallels. The other one is parallel to each other, equidistant again, but the degree changes because of the curve, right, path. Right now, rotate about a fixed axis, so the path, and we're dealing with only two particles. To simplify in your calculation, even two particles, oh my gosh, taking forever for you to calculate at this level. Yeah, so there are two, right? When and then two, dealing with the circular path. Okay, so you got it. Of course, you can move this particle anywhere in the body. Yeah. All right. No, this is just a single particle about that distance away from it. In reality, there are a gazillion of particles very close to each other. Since they're too close, that you can see their movement as a body from your human level point of view. But if you go into, let's say we're going to shrink yourself into the size of a particle and you go into that, right? Happening right here, rotating, the body rotating, you are going to be just a single particle right in there, moving along with all other particles around the rotating axis. Okay, so that's how you're gonna imagine yourself. Yeah, that's how to study. Okay, so when I say study, not just like rotation of all the axis, one a rigid rotates, blah blah move, and then you read it from here to here. That's not studying. Okay, so study mean you've got to go every word of it, and then actually think with it to the deeper level as far as you can go. Okay, so please do that. Um, Then the rest of the plane motion, okay, general is just a regular way of moving, not just a rigid 90-degree parallel and curve equidistant. Now you're gonna have a different tilted whatever, so we group it into general plane motion. So when a body is subjected to general plane motion, just plane from this plane to that plane down, so it goes a combination of translation and sometimes rotation. Okay, so it got more complicated, of course, here. So general, just take your line, different kinds of motion, and it can be all translation, zero rotation, or it can be all rotation, zero translation, or it can be a little bit of translation and rotation, like that. Okay, we're gonna combine all of them all together. Oh my gosh, yeah. So anyway, so right now you have three types: interplanar motion. First translation, we break it down into two types: rotation, and then translation or rotation combined. Okay, so at least you're gonna get that, please. Here is a picture, right? Picture of equipment and a mechanical, right, motion, and you can see it, and you can observe rectilinear, okay, rectilinear translation going on here. You can't see it, of course, but we're not going to ask you, okay, you're not at that level yet. Rectilinear translation, general plane, meaning rotation and translation. Here, rotation. Okay, because there's, look at this. See that circular path right there? Yeah? This is just a, when this move, it's like when you go, this is going to go like ding dong like that. Okay, this is going to go like this too. So here is again a curve, right? Translation because of the way that is connected, right? And then of course, here is another rotation. Okay, rotation. Here a translation, rotation, translation or rotation because it's going ding 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 like that. And then a rectilinear, all right, translation here. Translation, translation and rotation, rotation, translation, rotation. Okay, so that's a lot of movement even for this one single equipment. And of course, we're not even getting into these. Okay, this one is also moving, by the way, but it's okay. There's just a general picture of it. All right. Okay, now we look at it. Okay, how this thing is moving. So let's see. See that translation. Okay. Yeah. Translation here. Translation and rotation. Do it again. Rotation. Okay. Rotation. And then this bar, and that's your curvilinear translation. Do it again, because that's going, your two parallel lines is going that way. Okay, this thing going up and down, up and down. combine this thing rotating. Again, don't just concentrate on the rigid body. We are dealing with the points in that body, okay, all of it. And then here, rotation again. And you're dealing with the particles in that material, this hand, and also in here, okay? And here means this underneath of this part, okay? So there is a material part right in there, and then the bar, okay? So that's the movement that we are thinking about. All right, so now let's get into, this is just knowledge, okay? So we won't be doing calculations of this stuff. So your assessment is going to be like a very light calculation or understanding of the equation meaning, yeah. And at least you gotta know the equation, but I won't ask you to calculate with it, yeah, because I can get rid of the equation, yeah. At least you gotta understand when you look at it. So once you get your math ready, you can be able to calculate, yeah. So at least you gotta recognize, oh, this equation is that and that equation is this, at least meaning, please, yeah. That's anyway, that's we call it concept anyway, yeah. So translation in the XY plane, just listen, yeah, for knowledge. So we usually break it down into coordinate system. I'm going to make it really short for you, yeah. And then of course we usually use the points, because without the points it's really difficult for us to be able to calculate it. And most of the time go with the one single point or two single points, right, and three single points like that. So in this example we're going with the 2 points A and B, yeah. So as soon as you get the 2 points, you can calculate like whatever, yeah. So you always have to have the point, reference point, which is the origin of this x's, okay. So right now we're studying with the two x's, x and y. Of course in reality we have another axis, which is your z, okay. So the movement is actually very 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 complicated, okay. And you got to understand your chemical, right, knowledge, that the particles are in bond, right? They're loosely bonded. Some of them are okay. There's no such thing as a permanent connection right there. They're all just, because if you go all the way down to the atomic level, you still have space in between the particles in there. Yeah, so all the particles are just staying very, very, very close to each other. Yeah, so anyways, get the 2 points. As soon as you get the 2 point, we're trying to orient. Yeah, get the position or direction of it. When you call the direction, we deal with the vectors, because you got to think about how this thing is moving, in which direction is it going, this way, that way, this way, okay. So here it's just pointing, oh, here is my origin, it's going to go from here, bang, to there, yes, okay, like that. So if you get at least that kind of sense, yeah, you're okay in this course, yeah. Then I'm going to quickly go. Of course, in your test, I'm going to be giving you this equation, and you have to at least know that that's a relative position factor, yeah? Because this little r is position, yes? Little v is velocity, absolute velocities, yeah? Don't worry about the derivative or the integration, yeah? I won't be asking you. If I do ask you, I'm going to give you this entire thing, yeah, so you can put that in, and of course you know how to add, don't you? Yeah. So anyway, acceleration is going to be like this. Instantaneous acceleration is the same in translation, yeah. So in translation, motion, your position, velocity, acceleration are happening this way, okay. At least we know that, yeah. Up to today, yes, up to now, we accept this, okay? We accept these rules. So relative position factor, absolute velocity with instantaneous acceleration happening in your translation motion. And you gotta get at least that one, please, okay? All right, yeah, summarize your translation. Your rigid body is subjected to two different types of translation. Yeah, we study that way. One is 90-degree parallel to each other, move that way. Okay. Second one, move in a curve but equidistant to each other. Don't forget equidistant. Okay, translation. move with the same velocity and acceleration. And some of the textbook get confused with the curved linear, okay? Curved linear translation. Sometimes they don't actually show you the equidistance and mix with the different patterns of movement. So be very careful around that when you choose a textbook. In America, the textbook is just like everybody writing like whatever they want to write, and it's just very confusing. Sometimes depends on the publishers, and publishers are not obeying the scientific rules at all. Okay, so yeah, when we adopt your book is actually really good. By the way, I don't recommend change the curriculum. Yes, like I said, we can work with you if you. I mean, because even the school, we're running it like a business, so you're the customer, and of course we're gonna give you what you want, your grade and stuff like that, but professors are, like I say, we are the lifetime scholars. Yeah, so we study, and we're not businessmen or politicians at all. We're purely passion in studying. Okay, and teaching is just helping you, yeah, giving you what we have found out to you, so you don't have to work so hard to get to that point. Yeah, so it's just like my professor and professor, they give it to me. Sometimes you don't really get it from a professor, by the way. It depends on the professor. That's a student life. Okay, of course it's kind of like a family, so sometimes you feel like, and I like that, but don't feel bad about it. It just that okay, could you probably you have anxiety on your grade or graduation or things like that, I guess. So anyway, don't worry about it. Okay. So if you get about this much, I will be very happy. Yeah, your quiz and it's very easy, and mathematics also we reduce a great deal in here. Yeah. Equation I can change it because these are the truth that we have, right, with respect to all the scientists, mathematicians, right, physicists, they have found these things, so we have to respect. We can change it or abbreviate it out of it, or otherwise the meaning is gonna go crazy, wrong. All right, so this is just your concept, with the application outside. Of course, you can see this. Actually, there are so many bodies right in there, by the way, But of course, you're gonna simplify that, like your writers, on this wheel, which is your Ferris wheel, and we're gonna think about as a curvy, a linear translation. Okay, when you look at it, you're gonna think like that's a rotation, So curvy linear translation because they are going in curve, right? So let's just say, like, I believe that the author want to target this, okay, part of this wheel. Because if you go to this point, that's a rotation, okay? So here, if we think about this, that's, on the curve, so it's going that way, Um, we're just dealing with this circumference of the wheel, by the way. So these little things like that, even the author, and sometimes we miss it. So when you actually read it, the first thing you think is it translation or rotation, because you're dealing with a wheel and you're thinking about the circle right there. Yeah, it depends on where the point is, and I believe he is targeting this point. Okay, this 2 point on this body right there, not this body, because you have so many body right here. Anyways, just read it. So there's a gondola. See this gondola movement in a circular path in relative to this rotation axis right there. So it's going to be rotation, but if you go to the path, that's going to be curvilinear translation. Okay. Now you have to take my lecture. If you don't take the lecture, you will be missing out on all kinds of stuff. If you're just reading the PDF, handout is just giving you so you can print out if you want. Yep. Giving the lecture in class is also not very good because some of the student like absent. I can just talk it again and again to you. So just go back to the lecture whenever, like, if you're absent or something, to come back to it. But of course, it's mandatory that you attend the class unless you are sick, right? Sick or something. But this is an in-person class, so please make sure you keep your attendance. Okay. I still need to attend your classes, please. Okay, we'll get into rotation about an axis, yeah, fixed axis, of course. Another, yeah, just a theoretical thing. Okay, so the very thing that you gotta know right now, so when a body is gonna rotate, right, about a fixed axis, we're gonna go down into the body point again, and we're gonna pick a single point, yeah. So the point P located in the body is gonna move along. Again, the path is, since it is a rotation, your geometry is a circular path. Okay, it is a path because now we are targeting only a single point in that body. Okay, so now the angular motion of the body about the axis, we call like that, right? So the angular motion, why angular? Because you are dealing with a, let me get you a circle right here. Yeah? You're dealing with a circular path. Of course, the 2D drawing is not very good. Yeah, we can shape it like this so you can see the plane a little bit better. Yeah, make it a little bit lighter so that way you can see it. So anyway, so here is your axis, so we can put a little axis right there down here. They're not very good, but you can at least get it. Yeah, so the axis going around like that, and then you have your little tiny, of course, a particle. Yeah, right in there. So let's just draw a little particle right here. Yeah, it's a little bit D-shaped particle. I'm just drawing with my hand. Yeah, and then of course you're moving like two direction. You have this way or the other way you can move. So your counterclockwise and clockwise. Yeah. So when you do the, we call it angular because it's making a lot of angle right there. Yeah. According to like where the particle is going to be. So it can be here, it can be there, it can be there, and it can be there. Okay, so you can see how this thing move from point to point on this circular path. Your circular path is right here. There is so many angles. See, so that's what we're talking about, the angular motion. Okay, all right, so next one, let's go. So now of course we have a little better, yeah, textbook picture right here for you. So the angular motion, since the point is without dimension, another very powerful phrase right there, your point, all right, has no dimension. So you gotta understand what dimension is, why a point has no dimension. Think about these things, all right? At that time, it cannot move, it cannot have an angular motion, okay? Only lines or bodies and a goal and angular motion. Yeah, even if we call it a point, this one still have material, by the way. Okay, even though we call it a point, there's some atoms right in there, all kinds of, yeah, you have like a combination of atoms right there. If we think about the rigid body particle, depends on the elements that your body is made of, and it's not only a single element your body is made of, there's gazillion element right in there too. Yeah, so it depends on the body. So anyway, so again, a point is without dimension. It cannot have angular motion. Okay, only lines or bodies undergo angular motion. Now we'll get heavy into it. So when you think about the point, don't lose. We're not talking about just a point like we draw. It just that is the material of your body. Okay, some material. So you still have some particles right in there, even though we call it a point. You know, like how heavy, like when you have to think about it. Okay, so don't lose your chemical knowledge. Yeah, is there are substance right in there, particles right in there, more particles in the particle that we take it. Yeah, a point, but still it isn't a point. That's just still the bodies, by the way. Okay, so only lines or bodies undergo the angular motion, so going that way. Yeah, so the lines or the body. Okay, so since we are taking a point, yeah, a point doesn't have a dimension, so you cannot have an angular motion. only the lines, all right, and the body, this body, undergo angular motion. When we say body, don't forget the particles in the body, please. The particles are also the body, by the way. Okay, it's just a bigger body, a smaller body inside of a bigger body. Okay, like that. So anyway, so the angular motion. Right now, for simplification, we're just gonna take this body, right? And we're going to take the line, which is your circular path, right? And we imagine a single point on that line. Yeah, and that point doesn't have a dimension. So why do we have to do it like that? Is because for again for to simplify, yeah, when we do calculation. Okay, so we just assume, again, your assumption, we just assume like this is a particle, yeah, inside of a body. Okay, so now angular position is going to be from here to here, this distance right there, yeah, because we are targeting this little point P. So there's an axis right there, right? So rotation can happen. Rotation cannot happen without the axis. Again, this point doesn't move. It just stay there, yeah? And only this point in your body is going to move, yeah, on a circular path. So from here to here, that's the R, yeah, and we call that angular position because this is locating right here, that distance away from this origin. Okay, so that's, we call this angular position. And so many students always think like P is the angular position just because of, you know, like maybe confused with the term P as a point, but position, no, this isn't a position. All right, that is just the point because we are studying the motion of this body, okay, inside of this big giant body. So anyway, so but we're imagining this little as a point, okay? So here there's a line, and that line is going to identify where this point is away from the reference origin point on the axis O, okay? That many distance, so that's our distance, okay, far away. And we measure from, again, that is, we call it, I say reference point. Reference point is this, okay, from the or origin, which is on the axis, all right, on the axis of your rotation. And we call that R, right, the symbol R. So in the exam, I'm going to ask you what R is. You gotta know that's an angular position at least, yeah, even if you can't get the heavy meaning of it, yeah. Of course, don't confuse. I'm not going to ask you things like this, okay? Because that is a lot of yes, a deeper meaning into it. So I don't want to confuse you. That's, you will have to go up to, you know, a graduate level to be able to understand that, okay? All right. Again, I forgot to tell you, so dimension is meaning a point is without dimension. So don't think about like the outside common word of dimension in the movie. Okay, it doesn't work like that. When we say dimension, we're talking about it doesn't have length, it doesn't have width, it doesn't have a depth, it doesn't have a height. Okay, so that's what we're talking about. Yes, so it's just a single point. Where is the line? Well, there isn't. You know, where is the width? You can't make a width out of a point. You can't make a depth out of a point. But you don't have a height in a point. That's what we're talking about. Yeah. So some students are like so fantasized by incredible amount of this movie science. Movie science is not real science. Movie science is just actors and actresses talking because the actors and actresses are acting, okay? They just make believe all kinds of stuff. That's just like sometimes confused when they make the scientific movie. Some of them are right and some of them are not right, okay? So don't just get into those kind of stuff, right? And they're also internet, right? Whole bunch of misconception right in there. So theories are all wrong put together because they just want to make money out of it, or fame, or something, some influence that they want, right? So you don't want to get into it. You're at school, And even in school, some of the professors don't really, go into that anymore because you don't want to take it. So even for the teaching, it's really hard because even though we want to give you the real material, some of them don't want to get it because this is always stressed out with their life. Yeah. So anyway, so dimension, just understand that no height, no length, no width. Yeah. Out of a point, because a point is a point. Yeah. In geometry, this is a geometry sense. So yeah. So therefore, only your lines where you have some form of distance or length, the bodies, of course, you have width and height and depth, and go that angular motion. Okay, won't be asking you that level, by the way. All right, then we'll get into displacement. Of course, we hit the position, R is in an angular, displacement. So angular displacement, so displacing again from going from here to here with an angle, like movement. So you're gonna move from here to here that angle, yeah. So that's pretty easy. So when you move that angle, we're gonna just throw in the angular unit, like revolution and the radian, of course, to different units. And here is your conversion right there. 1 revolution is equal to 2 pi radian. Won't be asking you either, but you have to understand the unit is revolution and unit is radian, yeah, and they are connected this way, by the way. So I'll be asking this equation. I will be asking you even conversion, yeah. Yes, and this is like I don't know why like some students are so scared of the little d and little wiggly thing. That's just a symbol. It's just telling you it's moved from here to here, yeah, and move again from here to here. So from here to here. So since you're moving all the time, there's a rate of change of that movement, rate of change of that displacement, and that's all it's talking about. So in common sense, it's this point moving on a circular path with every time it moves, there is an angle change. Why? Because we're measuring that point position or distance, all right, from the origin. Okay, you gotta have some reference point to measure. If you don't have a reference point, there's no way for you to be able to measure anything in your life. Yeah, so that's all you need to know about your angular displacement. Then we're gonna get into angular velocity. Yeah. So angular velocity again is the time rate of change in the angular position, and we call that the angular velocity. All right, so the rate of change of angular position, okay, and we call that the angular velocity, and we're gonna give with the symbol little omega. Don't scare about the symbol. It's just a symbol, okay? That's just telling you angular velocity, right? And then we're gonna change the angle of it. That's just showing you like, all right, this d meaning like change, all right, change in the angle because your angle is always changing anyway, right? Here when your point move around the origin, which is this axis, on a circular path. Yeah, the angle is always taking changing angle, 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 right there. And we're going to represent this way, all right? So the velocity is, yeah, rate of change of position. Since the events are happening, right? So every time we get up and then, oh, here we go, so you can count from the 6 o'clock in the morning. That's your reference point starting time. 6 o'clock, to the evening. That's the end point. So all the events that you do, your movement, your things, your study, you come to school, go back to home, you eat at the restaurant or not at home. All of these are events, same as that. Yeah, this guy moving. See, so if you start like, oh, I am going to start, and usually the reference point, when you measure the movement of it is always from the human point of view is some form of a watch right there. So now your reference point is not on your watch. Okay, I'm going to start here and then about let it run about let's say 0.1 second for this to come back to here. Yeah, and like, oh yeah, 0.01 point second, this thing is going to go from probably like here, let's say like that. So your reference point from 0.1 0 second to 0.1 second you're measuring. So when you give that and you take a look at it, there's a van in there because there are always a van in the real life, right? Because we have a space and we have existing, it's just there. Yeah, it's just there, right there, it's just popping out of we don't know. So we call it the origin of the all the existing coming out is the point of null, meaning there's no point, but just it's just come out from something that we don't know. So since you don't know anything, we imagine the beginning of the everything is nothing. Okay, so like that we imagine. So anyway, and this is the center point, right? And that thing is going, and you give the measurement, your time, equipment, your watch or clock or your phone, and then you give a start, the first reference point 0, and then count all the way to 0.1 second, and you cut it out, and and let this thing run, right? So it will run from here to here. So the movement happened, right? And one event happened. Okay, so when the event happened, let's just say your time measurement in your clock is 0, and then you're going to cut it at 0.1. So that's the amount of little tiny, right? And at that time, it's going to move from here to here. So the position this point has taken is this, and that. Yeah, so that's a change of position. Okay, because the event happened, it moves. It moves from point, dot, dot, and ta. So that is telling you my position move, yeah, in that amount of time. That's your reference time right there, wherever you're measuring with, okay? And we call that angular velocity. Yeah, how easy that is. So don't worry about this little d and this and think about calculus. I don't want to get. I can change this equation. Yeah, it would be like academic. Yeah, it's a violation. Yeah, we can change the curriculum. That's academic violation. If you want a different textbook or a different way of teaching, then yes, even the textbook doesn't exist for dynamics, for pure conceptual, even though we force it anyway. Yeah. So yeah, don't ask for things that doesn't exist, by the way. But we will work with you, okay? If you worry about the big, heavy calculations, and then we go easy one, yeah. But cannot be able to change the equation, by the way. Yeah, because that's against the scientific rules. So professors, we're scholars. So scholars are bound. So as soon as you graduate PhD, you have to take a vow, just like you take a vow by the physicians or lawyers. Yeah, we have to take a vow. We're not going to do anything that is in violation of the scholarship. Yeah. So anyway, so this equal to this and this. Yeah, change in position. Change in position. We're always against time because all the events, as soon as the events are happening, the existing is the time. Okay, all right. So let's go back and happening in that time. Yeah, reference again. Reference point from here to here. So let's go back to angular acceleration. So angular acceleration again, go on about the rotation or axis, and then there's a path, a circular path. Something is moving, and we narrow it down to a point, studying with a point in a rigid body. Yeah, the angular acceleration again, another symbol. We call it alpha. Yeah, it's going to measure again what is changing. Velocity is changing, and here we go. Yeah, student, right? We human, most of the average human intelligence stop right there. We okay doing this. Okay, we can like totally get it for the rate of change of position. Yeah, easily can be able to see it. But when we get to velocity, here we go. How are you going to imagine the velocity in your brain? How are we going to picture it? There is your frustration. Okay, so don't worry about it. So when you get from position to velocity, our human intelligence get disconnection with the picture diagram or images in our mind. Okay, don't worry about it. All you have to do, you have to link it to back to your position here. Okay, so your velocity is happening how, again, something that you can't draw it in your diagram. That's why you can see the velocity. You have to feel it. Okay, you have to feel it by doing it. Yeah, by yourself, like by moving yourself. You can really feel the velocity acceleration by driving in your car. Pay attention when you drive. Don't just listening to the music or doing something. Yeah, so when you drive every day in your car, feel that acceleration, feel that speed, and feel that velocity, because velocity acceleration can only be felt. Okay, it cannot be drawn, by the way. So that's why you have a disconnection when you get to velocity, when you get to acceleration. Okay, so anyway, so that's a rate of change of angular velocity. Okay, the rate of change of your angular velocity. We put this a change thing symbol right there again, d. Yeah, oh, what is changing? Velocity is changing, and then measuring in our reference time point 1 to point 2, and we call that just a time, yeah, change in that time, and this is happening, and we call that acceleration. Okay, so if you get this, I'll be very, very happy. Yeah, of course. And then we're gonna link it back to the position. So we're gonna describe the acceleration in terms of position. So you have to go 2 times. Of course, there's a rate of change of position happening, and then there is a rate of change of velocity happening over that rate of change of position. So therefore, you have a 2 rate of change going on. One is a position, and the other one is a velocity of that particle taking from one position to another position. Okay, that's it. I mean, how easy that is, yeah? So you put 2 in there because the 2 times going on right there, yeah? Okay, all right, so and now you're gonna fuse it all together and use your yes, a mathematic going from here to here. I won't be asking you, okay? This is just a plugging in on the we call it the we like just changing the place in the equation, yeah. If I put it in a simple way, yeah. So we're putting this, okay, with this after, of course, solving it. But of course, we are not going to ask you going from this and this to here at all, okay? So don't study that, okay? I won't even be asking you this, okay? But I might ask you that. That's a simple one, yeah. At least you should get it. And then, of course, we're gonna bring in our kinematics from the first, right? Not the rigid body, but just a regular kinematics, the first chapter. So your velocity, your acceleration, and then your acceleration, which is the same thing, by the way, yeah. But of course, we're not going to be asking you to here. At least I'll ask you this and this, yeah, that and this. Okay, this knowledge, so showing you real life outside, it's just all rusted because they run it all the time. That's just a gear, yeah, gears, and operating in a mechanical operation. We call that the crane, and they're rotating about again, axis here, axis here, axis there, and axis right over there, yeah. See that? And circular path, of course, circular path. Where is your point inside of that material, yeah? When you look at it, it looks like a rigid body, but they're not really rigid when you go to the particle levels, right? Atomic levels. They're all moving by the way inside. How strange that is, but they are. Yep. Okay. I'll go back into here. Constant angular. Then we study the different types of acceleration, and when the acceleration is moving with the same, yeah, for a particular amount of time, then we call it the constant angular acceleration, okay. And at that time, of course, if your angular acceleration is constant, your acceleration is going to be the same as the first acceleration, yeah. So your second acceleration is the same as your first acceleration, so as you take a different position, yeah. So that's the same thing. And here, these things are, we're writing our regular kinematics, right, in the form of rotational kinematics right there by changing the symbol, but they're the same. Yeah, your acceleration here, your velocity here, your position here, yeah, and then of course velocity and acceleration. So you can you can match it, you know, back to the regular kinematics equation. Then you can be able to see the only thing that is changing is your symbols, yeah. Okay, now we're going to narrow it down to motion, right? Motion of this little point. Of course, again, we are imagining this like a material. There is a material on that point, okay? What is the material? The material of that rigid body material, the same material. So now the rigid body is going to rotate about an axis, and the particle along this is not moving, by the way, so we can just make it an origin right there. So because it isn't moving, so we can use as a reference point. It's going to rotate, so the point P is going to travel along a circular path of radius r, okay. So that radius, we call it radius because this is a circle, yeah. So we bring in our math knowledge right in there, because from here to here is your position r, right? So this position r is actually mathematically the circle's radius, yeah. The center is O, so don't forget the position. All right, we give a little theta, circle, radius r, okay. R is the position, change from here going to there, we call that change in positional P, because position P move from this point to that point. Yeah, so from here to here we call this, yeah, change in position. Distance from here to here, another, yeah, the position is here. The distance from the origin to here is going to be your R. All right, so that's a motion of point P. Rigid body rotates. Point P inside of the rigid body is going to travel along a circular path of a radius R with a center point O. Center O, radius R, point is right here, point is inside of the rigid body. Rigid body is rotating, the point is in motion. Okay, what kind of a motion? It is a rotating motion. It is going on a path. That path is a circle. The distance is R away from the origin. The origin is on the axis. Okay, you have to get that one. So when you study and do that, you know, like I am telling you right now, and of course how that is rotating. Okay, this is right now we're going this direction from here to here. Yeah, and here your this is your velocity is happening right there, which you can only feel. This body can feel that, but we can't really draw that. Okay, we can draw the velocity, by the way, but we just put it right in there. It's there. Yeah, it's right there. The angle, yeah, as because it is a circle, so therefore there is angle. Yeah, since this is the axis, we can also get an angle, yeah, of this position from there. Of course, I won't be asking you that, but you know that there's an angle that is that angle away, this angle away, but we'll concentrate right there. Okay, so two different angles right there. Look, this is a displacement right here, by the way, from here to here going. Yeah. All right, so now we're going to take that circle out and then draw it on a 2D flat plane. You're going to get center, distance, position, your velocity. Yeah. Okay, position and displacement. Position is just a position. Displacement means the position is going to move from one point to another. Yeah, it's going to move. And when you bring the time factor, we call it the rate of change of displacement. Every time we bring the time, it comes the rate. Yeah, so the position of P is defined by the position factor R again. Yeah, and here is your confusion, all of it, because this is we're going back to our regular kinematics, right? So don't confuse this R with that R, by the way, all the symbol. Oh my gosh. Yeah, so position and displacement, the position P defined by the position factor R. Position is a vector because it has direction. Okay, not only distance, move from one point to another, it has a direction where that thing is going. Yeah, so it's extend from your O, okay, to the point P. So if the body rotates, right, so this is again your displacement, so this is a change of position. All right, then of course that's a angular, this is just a regular. Then P is going to displace this much. All right, so regular kinematic, change in position, angular, change in position. All right, but for angular you have an R. Okay, where is the R? It's just right there. In angular we call it the distance. Okay, the distance. In regular kinematics, okay, is a different thing. Okay, so here position P, position factor R, this is a vector, position factor right there. Okay, extend from, I think I should just copy this thing. Yeah, I don't know why I can copy. So just fix into this. Let me copy this. Okay, so I got this copy. So here, yeah, so this is your origin. Yeah, this is your distance, angular, but then of course we're gonna call it a vector because its direction is changing as it moves with a particular angle. Yeah, angle around this axis. And of course your velocity is there and your position is going to move like this, and every time we move the position we call the delta right here. Okay, so delta means like it's a change, and then your theta. Yeah, where's my pen? So anyway, so I can draw this little point, just it's not the same scale, but you get it. Yeah, so like that. So your R is changing this angle, and we call that little theta. Of course, it's changing, so we put D right there. Yeah, so this D is that guy. Yeah, then your point, of course, is gonna be no. Your point is here, no. Da 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 da. Yeah, and it's gonna displace, right? Displace. So this is change. This is your regular kinematics. Okay, don't forget that. So change in position. This is angular. Yeah, change in position. Linear, like this. Change in position. We're just linking. Yeah, relating. So this is just a change in position in a regular kinematics. So go from here to here is that. So this one is this. Okay, so don't forget, the only thing that is different is you have a distance away from the origin. Okay, because you are rotating this around the axis, so we have to calculate also. We also have to calculate that factor right in here. Yeah, so this and that is equal to the regular kinematic ds. Okay. We'll go to the next one. Okay, so from here, I just listen, and we will. I might ask you only just a very very simple equation. Yeah, I'm not going to be asking like very complicated one. So now we'll get into the velocity. So what you just listen, yeah, how it's going. If you get a little bit of concept from here to here, I'll be very very happy. Yeah, you don't have to remember all of that. So the velocity of p has a magnitude, right? So magnitude means it's just a value. So at this point, now we get into the velocity, and we can calculate by using this. Again, this is your regular kinematics, and this is linking to your angular kinematics, which is position anyway. And again, we are going to bring our time, because everything in the world is happening, existing, okay? And we are throwing in from our human perspective reference starting point and ending point. So every time we throw the reference starting point and ending point, we call that time. So outside the movie, people get it from some science, and then scientists give it to them with a common word, and then they interpret it in some wrong way, and sometimes right way. But whatever that is, we can call it time doesn't exist. Everything that is happening are events. Time is just a human mate with our intelligence, in our brain. So that's all in your head is what exactly it is, it's just like the existence just right there, way before we ever come into existence. All right, so when we come into existence, we have a nervous system, and with a brain, so we think and we observe what we are in it, what we are in, and some stuff happening, so we start measuring, civilization after civilization, and human become it's a starting point of a little cell, and now we are human. Of course, some people think like we're just bang as an angel, related to God, and it's come right here appearing. What you can think whatever you want to think. In science way, it's just this particle just come together because of the forces in the universe, and some aggregate. And when they aggregate, some of the particles have a little body, some of the particles have a bigger body, some of the particles have a fascinated body like us. It's very very complicated and has more power in it. And if you want to see that as a divinity, we are something actually. So in whatever way you want to look at it, it's the same thing, by the way. With God in it or without God in it, it's the same thing, because this is what we've got. Whatever that is. Now let's go into here. Your position, regular kinematic, your position, your position change of position. All right, angular kinematics. Rotation, we call it angular kinematic is your rotation. Another common word that we use. And then of course your time, yeah, your reference point of the events happening from this point to that point. So when you do that, we get this. Okay, so the direction of your velocity, okay, is tangent, yeah, to the circular path. Why do we have to bring the regular kinematics to the rotational kinematics? It's because two things going on right there. One is the angular velocity happening when it is moving, and there's another type of movement which is just a regular kinematic, which is going, yes, this, right? So you can break this path, circular path, and just line it up like that. Okay, so from here all the way to here, yeah, that path you can break it into just one line. So your P is gonna be right there. Yeah, moving with the velocity. So therefore we bring the regular kinematics, okay, along with the angular kinematics right there. And then of course we show our relationship right there. So our relationship, second relationship, regular kinematic V is equal to angular velocity and angular position right there. Yeah, that way. So in abbreviation is that, yeah, regular kinematic velocity going here is equal to your angular kinematic, which is going on right here. Yeah, like that. All right, and with a reference to the origin, R. Yeah. Okay, so now let's go into another one really quickly. I don't have time anymore. I might cut the lecture two part. Yeah. All right, acceleration, the same thing. Yeah, acceleration of P, we're gonna express in terms of its normal tangential again, because we're linking the regular kinematics to the angular kinematics. Your position, yeah, acceleration is happening right here, yeah, on this line, of course, line, yeah. Of course, your P is right here, and the linking is relationship is like this: regular kinematic, angular kinematics. Okay, every time we do angular kinematic, there is a reference measurement is R from origin all the way to P. Yeah. Now we can write it this way. Yeah, this is just for you knowledge. Okay. Don't worry about these things, yeah, but if you carefully read it, this is reiterating the same thing, yeah. So regular acceleration is a change in velocity over time. Angular acceleration is a change in angular velocity over time. Yeah, only the where that velocity is different. Yeah, so angular velocity is here and regular velocity is there. Yeah, okay. Then of course this is just showing you like a derivation of your series of equations here. Yeah, don't worry about it again. I am not going to ask you. Yeah, so you can just read it for it. Not going to ask you any of it. Yeah, it just showing you, oh, okay, here we go, we have two different movements going on, rotation, first origin, second origin. We have a 2-point going on right there, because you got to deal with this 2 gear, by the way. Yeah, so now we're starting with the little points each on each gear right there. Yeah, gear is your circle, so therefore it is in rotation, so that's we call it, yeah, angular motion of this particle, of that particle. Yeah, and then we're gonna put in the alphabets right in there to show where that particle is. It's a RB away from. Yeah, and then of course this is a gear, and that's a B gear, so RB away from the center, and here is a RC away from the center. Okay, and then of course you have two different, yeah, circle, yeah, first circle, second circle, and then the point of contact right there. Yeah, so again, tangential is along the path of the circumference of your circles, so you have two tangent components going on because you have two circles right in there. Okay, and then also you have a normal components of the acceleration, which is your regular, yeah, regular velocity and the regular acceleration, and these are your angular velocity, angular acceleration. Okay, and we're giving you the relationship of it, and you don't have to go into it. And if you get what I have just told you, you're okay. Yeah. So don't confuse yourself too much. When I ask you to list the equation, you're gonna just list what I ask you in my lecture. So if you're skipping the lecture, you're not gonna know, and you'll be giving me all kinds of equation. Yeah. Another, yeah, different types of movement. 2 gears studying. Yeah, here is your tangent. Yeah, your velocity, regular acceleration, and then you're gonna link it to your angular, right? So just showing you the different types of motion here. Then we'll get into, this is just an important point. If you just read it, okay, I am not going to ask you any of it or yeah. I'm going to ask you what I cover in my lecture. So that just read. You don't need it because it's just a heavy calculation for it, procedure for analysis. You don't need it, okay? I might ask you this one because I already told you this one. Yes, that's just angular, yeah, kinematics right in there. The V and A and S in regular kinematics. Okay, about this much I might ask. Yeah, I might ask you this. Okay, and I will not be asking you any of that for you. Yes. I won't ask you analysis at all, yeah, so you can just read it, yeah, and that's just a picture showing you with the real-time, yeah, example outside how we calculate the motion. If you can get it this much, okay, but yeah, don't stretch yourself in it. Procedure for analysis, again, not going to ask you any other coordinates, right, breaking coordinates and studying, okay. Time derivative, again, won't be asking you either, yeah. Time, if you get it, like time is just a measurement, and we usually study the time in between 2 reference point, if you get it, and the events are going on in between there, yeah, and we're just looking at what events are going on in that 2 reference time, in that 2 reference point, and we call that time. We measure by using equipment, human equipment, by the way, okay. So if you think from the perspective of the existing, it doesn't exist. All right, so rounded motion analysis, velocity. So again, we're not doing the motion analysis as a heavy calculus right in it. So all you have to do is just get the concept and theoretical, yeah. So if we want to do the analysis, yeah, of the relative motion, okay, you go back to our general plane motion of your rigid body, and then we are going to combine translation and rotation. If you get that, that's all I want you to get it this, okay. So relative motion analysis, every time we think about the velocity and stuff like that, and we want to analyze, what are we analyzing? We are analyzing the combination of the translation and rotation motion, okay, and that is your general plane motion, yeah. So general plane, so GP motion, GPM, okay, is a combination of your translation and your rotation, okay. So if you get like this, see like how I always draw and put it in my own word. If you get that, okay, yeah. So this is contributing. So translation and rotations are contributing, yeah. Plus is for combination to the general plane motion. So draw a diagram. Don't lazy. This is not English class, okay. You can just read the language and put it in your head at all. You have to read, draw, symbolize by yourself, and then I'll link it to the deeper meaning of it, okay. All right, position, again, going back, the same thing, yeah. Here, and because you have 2 points there, so right now we're showing you going from here to here, yes. So you have your origin measurement, yeah, this distance, that distance, far away, okay. So actually I'm getting it, yes. So I'm going from here to here, yeah. So R and B, so the direction is going this way, your vector is, okay. And we're going to translate, so mean like translate from here to here. Of course, there's another imaginary plane right there, line on it, yeah, from equidistant to each other anyway. So we're going to translate. So if you translate, we're going to get that. So the position factor, yeah, RA. And then you also have RB, okay? So that's just showing you this position and that position in reference to this. Okay, so how do we describe this? Yeah, a distance from here to here, because you're moving from here to here in reference to this origin. Yeah, so therefore we gotta use this, okay, instead of a regular linear point A to point B, that distance away. Okay, so in linear or regular kinematic, it's easy from here to here that you just go and measure it. Yeah, from here to here is right now we're dealing with from a reference, a planar. Yeah, a planar translation. So therefore your measurement is subjected to this center point right there. So therefore this R coming in. Yeah, so that's why your brain, when you think about this too much, and then when you gotta move it to this, and you have a confusion right there. Yeah, or you have to just add it up. Yeah, so you will have to add. So but when you add it, they are vectors. Okay, you can add it like from here to, let's say this is 5, and then you say like, oh, that's a 5 units away. You can do like that, because that's just a idea idea that we study, and that doesn't exist in the real world. In real world is this. Okay, always there's a reference point that you measure from. So therefore there is a direction, because you have a 360-degree around direction, right? Up and down, yes, front and back, yeah, so all 360-degree around directions going on. So you have to add it in a way of the vector addition. Yeah, so yeah, I won't be asking you, but if you at least know theoretically going from here to here, subjected to the center, we have a 2 vector, we're adding the vector in order for us to get that distance. Yeah, if you get that, okay. Yeah, all right. Displacement, again, I won't be asking you any of this. Okay, this is just showing you that one is due to the translation and rotation. This one is due to the translation, and then this one is due to the rotation. Okay, about that point. So where's my pointer? So if you can get about that much, yes, I'm gonna be very happy. Yes. So here, if you can't see it right away, don't worry about it. Okay, see, look at this. See, look at this little one right there. Yeah. Here, yeah. So I might ask you only this. Okay. So you gotta know that, okay, this guy is right here. I might give you this pixel, yeah, and then this guy is right there, yeah, and we're translating, and the directions are going that way, and we're moving band that way, okay. And this one is a rotation, yeah, due to rotation about that axis. It would take you some time for you to be able to see it, yeah. I can go a little bit slower for you. So see that point A, yeah? And we're translating, yes, from here to here. So I won't be asking you that complicated. Yeah, this is just a general motion. So if you look at the diagram, you should at least get that, okay, there are a lot of motion going on, because I have a translation here, yeah, translation there, and then translation there. It's a combination of 3 different direction or movement going on right there in time, t to time t plus a change in time. Okay, so if t is 0, yeah, your change in time is like a 5 seconds. So that's what it's saying, 0 plus 5. Yeah, change in time is 5. General plane motion, again, if you think about the general plane motion, if you know that they are a combination of rotation and translation, you're fine. Okay, here the same thing, yeah, different translation and rotation. This is just showing you the outside, yeah. So here, look at this, the center, yeah, and this is your wheel right there. Okay, so you know the angular velocity. This one is going in that direction. Even though we show it at the center, you can also put it on the circumference. It doesn't really matter, you put here or here or here, that's the same, okay, because it's the same rigid body anyway. Don't forget about the points inside of the rigid body. That point can be here, 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 or here, or here, yeah. um, um, on the circumference, okay, or not on the axis for the point. For velocity, you can put the vector anywhere, okay, because it's just going into that direction. Well, that's what we're, like, if you get like about that much, I'm okay. Yeah, just theoretically you'll try to get it. Not going to be asking you any of it. Velocity, the same thing. Yeah, if you just read it one time, that's okay. Won't be going into it because your course is a different thing, different level. Yeah. A general plane motion. The only thing I want you to get again, yeah, is the only thing I want you to get is a combination of rotation and translation. Yeah, different kinds of movement right there. Translation, rotation, general plane is both of them. Yeah. If you can be able to see it on the picture, all right. So if I ask you like, hey, what is this? What kind of motion going on? You gotta tell me, oh, that's a general plane motion. Yeah, at least. Yeah. And here is a vector addition. So if I give you this equation, yeah, you gotta tell me what they are. Yeah, that's a velocity, point B, velocity, point A, how easy that is. Yeah, and then that's a velocity of B with respect to A. Yeah, B with respect to A. All right. Vector diagram, where they're pointing to. Yeah. But again, I won't be asking you for calculation or any of it. I'll give you a little diagram and ask you what kind of motion can you see in there. You gotta give me, oh, that's a rotation because it is rotation. Oh, that's a translation because it is translation. Yeah, showing you. About that much, of course. And then the same thing with this. Yeah. So if I give you this equation, you should be giving me that's a velocity of B, velocity of A, base point A. Yeah, this is your base. And then your angular velocity in your body, and then that's your position. Yeah, that's a position vectors. A little animation right here, picture, where the velocity, angular, your center, okay? Velocity, base point, meaning we call it base because we're just putting that point at the base, yeah? If you look at it here, rotation, at least you gotta tell me, oh, that's a rotation motion going on right in there. Procedure for analysis, we don't need it. Just read, okay? Won't be asking you any of that. Velocity equation, again, at least you gotta get this, and you have to get the velocities are, put that into formula by vector combination, right? Addition. So if you get that, I'll be very, very happy. Instantaneous center of a zero velocity. So instantaneous center of zero. So zero velocity meaning there's no velocity at that point, okay? And when we do the vector addition, we always have to come up with a base point, yeah, a velocity, and that base point is right here. And at that base point, there is no velocity, okay? The velocity is zero at that point. The rest of them we measure, right, along with it. Yeah. So at least if you get it, that'll be okay. So that's base point. It is a point that has zero velocity. So if I ask you, go ahead and point out where the base point is. It's right here, yeah, on the base. And then I'm going to ask you, like, oh, okay, do we have a velocity at there? No, there's no velocity. Why? Because we are imagining that point doesn't move, okay? It doesn't move, and we're measuring, we're calculating and measuring in reference to it, okay? Location, not going to be asking you how to calculate the location. If you get it, it is at the base, you're okay, yeah? Formally, we define that, all right? IC is, so anyway, I won't be asking you this. If you get it from here to here, yeah, that's okay. So velocity of a point on the body is always perpendicular to the relative position vector directed from the IC. I can show you, like, actually, we'll have to go back to here, yeah. So I have a, like, actually, let me go and get that little. Okay, so here I bring this picture for you. So now you can see. So when we say, where's my pen? Okay. So when I say perpendicular is this. Yeah. So this is what relative position factor. Yeah. And then r, of course, and then the velocity is this guy. Yeah. It's perpendicular. That's what we're talking about. Yeah. So to locate the IC, we can use the fact that the velocity of a point on the body is always perpendicular to the relative position vector directed from the IC to that point. Okay, so it's right here. And your IC is right here. Your vector is right here. It's perpendicular, yeah, to R. Okay. So make sure you get the instantaneous center of zero velocity in theory only, no calculation. Won't be covering any of this, right? If you have time, you can read it. This is also calculus, everything. We don't do that. And you can't do any of this either. Okay, so I might ask you where is the IC, okay? So all you have to just point out where the base is, which is here, yeah? And this is a little more complicated than that, so I won't be asking you. So right now, just I will be asking you the IC at the base point, all right? So which is a little bit easier for you to understand. A real life example, yeah, we have a board and then slides downward to the left. Yeah, here's the board. It is slides downward to the left, but when you look from your human vision, it looks like a right. Yeah, but you gotta actually look it from this board side of vision. Yeah, so that's on the left. Your right is left. Okay, and then general plane. So here, your IC is right there. Yeah, won't be asking you, it's just showing you that for you right now, and your velocity is right there because it's perpendicular this way. Okay, and of course r is distance r away from each other. You might not get it right away, but if you get only one, I would just give you your IC at the base point, yeah, in your exam, so that way you know that it's perpendicular to your r to the center because you're familiar with angular stuff anyway. So and then your direction of the V is right here. So make sure you get at least this. Okay. All right. Procedure for analysis. No, it's not necessary for you in this course. Relative motion analysis, again, we're just going, yeah, with the regular kinematics, yeah. So bringing the kinematics right in here, and then we're gonna move from position to velocity to acceleration. Okay, I think I accidentally paused it. Yeah. So anyway, so go back. So don't you don't have to study this. If I'm repeating, I'm sorry because I forgot to turn this back on. All right, and then the window, I think I explained that to you. Yeah, so you need the energy to support this weight of the window so the window can stay right here and open position. So in order for that to happen, we have to work with the rotational and also the regular kinematics all together. Yeah, here we get into again relative motion analysis, not covering this. You don't have to study that. So just go. We usually study the kinematics on position and then velocity and the acceleration. They are very, very heavy math, so we won't be covering in your conceptual course right here. Yeah, but I can't get rid of them because you have to at least know that, aware that they are there. Okay, so when you come back to it, it is going to be there. As you study, of course, if you want to continue to study. If you don't want to continue to study, just forget about it, that's fine. And here just showing you, yeah, outside picture, and this one is going to lift up and down here, yeah, supported by your engine fuel right there. Of course, you can control, yeah, from the dashboard right here, yeah, driving board. And then this is also dealing with the relative motion analysis where we can produce the enough energy to support that weight, yeah. And we play with, of course, kinematics because you're moving it. Yeah. So anyway, so that's all for rigid body. Yeah, planar motion. And make sure you study only what I cover and do not study what I don't cover. Do not go into all the equation I did not cover in my lecture, and so make sure to take your lecture without skipping it. If you're skipping it too much, then you will be missing a lot, and you won't know which one I will ask and I won't ask, and then get confusion and get a panic attack and go on to somebody right there. Yeah. So make sure you take my lecture. These are not just my material. This is actually the school material, because school adopted this textbook and it is bound to the curriculum. Yeah. So we will show you, and of course there's no such thing as because dynamic mechanics, right? It's calculus. There's no way for us to get rid of it, but if we want to make it concept course, then I'm gonna just ask you the theoretical stuff. Yeah, theoretical stuff with the easy question for you with a minimum amount of calculation. I might even not going to give you any kind of calculation for this, for the chapter 16, okay? Because it's too much of the heavy calculation right in there for you. And if I do give you, I'll just give you the value straight out, and all you have to do is the algebra, yeah, adding or subtracting or dividing or multiplying, okay? So mostly adding here, by the way, so dealing with the vector stuff, yeah? All right, that's it for today.